In this lab, we focus on understanding the motion of a falling object. Newton's laws are once again important in the concepts covered in this lab. A falling object in a vacuum would be subject to just the force of gravity pulling it downwards. And in the experiment we conduct, trackers used to analyze video frame by frame and plot the falling object's y-axis position versus time. Using LowScript VPython, we can create a more precise computational model using observations and formulas derived from the experiment in the code. We create two different computational models for measuring the position versus time of an object subject to only the gravitational force, and another model where the object is also affected by the drag force proportional to the square of its velocity. Now, the initial position and time can both be gotten from tracker. So the initial position in this case has a vector 0, 0, 0, and the time is 0 seconds. The initial velocity of the ball is 0 in this case because the paper ball which I used in this experiment was dropped from rest. The last observation time, or the total time of the drop, was 0.400 seconds. Now, looking at my tracker video, this is what it looks like. Alright, now, the code for my computational model without having any drag force is here as shown. The proportionality constant used for the magnitude of the drag force is 0, which means the drag force is 0, right? So the delta time that I input was 0.400 seconds, which I got from tracker. The net force in this case is simply just going to be the gravitational force, because this is theoretical. So we have the negative minus the mass of the ball times the gravitational acceleration times j hat. The formulas to apply the momentum principle stay the same consistently through all the code. To update the object's velocity, in this case, stays the same, and updating the object's position line. Now, looking at my other computational model, I have a proportionality constant of 0.0003, which I found was most accurate as the computational model graph was most similar to my experimental model graph. To calculate the net force had a different method in this case. We have to calculate a drag force separately, which is a proportionality constant times the y part of the velocity vector squared, and we need to add that to the weight force, which we calculate in the original code as well. Adding those two together gives the net force, and updating the velocity and position stays the same. Now, looking at this on a graph, position versus time shows this. As you can see, all of them curve downwards. So the line for the computational model, though, without drag is decreasing more steeply, the red line, towards the end than the experiment data line, and the line for the computational model with the drag force, as they should. Seeing this on the velocity versus time graph better shows this. If I scroll down right here, the line for the model with no drag force decreases with a constant negative slope, this red line. The only acceleration vector present for the red line is that of the gravitational force pulling the object down. The line for the model with the drag force starts to curve upwards at the end, indicating that there is air resistance slowing down the object and that the velocity is approaching its terminal value. The experiment line more closely follows the model with the drag force. Now, what if we throw the object downwards? If the object was thrown downwards, there would still be no change in the terminal velocity itself. There would simply be more air resistance to counteract the force of the throw, and the object would reach terminal velocity more quickly. Drag force, as it is proportional to the square of the velocity of the object, would be higher. And you can see here, I added a small force of, let's just say, of a throw downwards, -3 newtons in the y directions downwards. Adding that to the net force and running the program looks like this. As you can see, the line becomes flat at the end, indicating that there is a slope of 0 near the end.